What are the ways in which we can use Einstein's field equations in our daily life? What are the practical applications of this equation? A cup, a piece of stone, a heavy truck, an elephant, all of these create curvature on the surface of Earth. Can we use Einstein's field equations to measure the curvature? What actually this equation helps us to measure? Is there any use in our daily lives? Well, I'm going to answer all these questions, and in this video we are going to see how, where and when Einstein's field equations have a practical usage. We are also going to find out the actual usage and the application of this equation in our practical life or in other branches of science. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to General Theory of Relativity, practical application of Einstein's field equations. So first let us look into what are the topics that we are covering. So we are covering, first we need to know what does Einstein's field equations measure, what is the curvature of space-time, and how much actually is the curvature. Can we calculate the curvature which happens in our daily life using this elegant equation? What are the practical applications of field equations? How can we at all find out some of the solutions? What is called a linearized gravity, and what are the solutions from the weak gravity metric? So first let us see what does actually Einstein's field equations measure. So you see, this is basically the field equation of Einstein, which is the pivotal force on which general theory of relativity depends upon. So if I take component by component, the first R is actually called the Ricci curvature tensor, and it gives us an understanding on how a volume of the matter changes when it moves from flat space to curved space. Then we get another R, which is called the Ricci scalar, which keeps track of how the size of a ball deviates from Euclidean space when it moves into non-Euclidean space. Then we get something like G, small g. This is the central important part, which is called a metric tensor. It is a way of measuring all the causal structure of space and time. Then we see something which we cannot see in here, but it's a contraction of the above two tensors, which is called the Riemann curvature tensor, and it is a tool to describe the curvature of Riemannian manifolds. This is hidden. And finally what we see is this T, which is called the stress energy momentum tensor, which actually describes the matter movement through space-time. These are, in very brief, in short, the different components of Einstein's field equation. If you really want to know more about each of these components, you can go to my playlist in General Theory of Relativity in this channel Physics for Students, and you can find out further details. So we found out Ricci curvature tensor, Ricci scalar and other components, and these are actually the signs which exist in Einstein's field equation. Okay, so here we see that there is some constant which is the capital lambda, which is called the cosmological constant. We got C4, which is the speed of light. Now you might be asking why it is C4. For that I need to make a separate video on the dimension analysis of speed of light. This 8 pi is a constant. This G is also a Newton's gravitational constant. So these are all the constants coupled with certain Greek letters and tensors completes the Einstein field equation. Okay, so let us also look into something very important. This R mu nu actually measures the dimension in space-time. So this has got 4 dimensions, as we know. 0 is the time axis, y-axis, z-axis and x-axis. Similarly here, this G mu nu is also 4 dimensions in space-time. Again, it is a 4 dimension in space-time, and this one is also 4 dimension in space-time. So if you can count, you see 4 plus 4 plus 4 plus 4. This gives, this mu nu are basically the indices which calculates the dimensions of space-time, and we got total, what we are looking at, a single equation is a collection of 16 partial nonlinear differential equations. Okay, so the Einstein's field equation, as we can see over here, this part as we can see here, it actually measures the curvature of space-time. That means how much things are curved. That is basically the geometry of space-time. The right hand part is the stress energy momentum tensor. That means whenever a matter is present in space-time, it measures the matter of the energy content, that is the matter of movement. So the curvature of space-time and the matter movement are both equated by an equal to sign, and we can summarize that space-time tells matter how to move and matter tells space-time how to curve. So before we go into the practical applications and whether we can measure Einstein's field equation, it is very important for us to understand the components of Einstein's field equation, which measures the curvature. Now when we tell that Einstein's field equation measures the curvature, what actually it does? Can we measure the curvature that we are sitting on a sofa or a book is lying on a table? Let us look into the next part of our video, which tells about the curvature of space-time. Okay, so let us take a demonstration of this plan. I think it's a Superman standing on the surface of Earth. Obviously, this causes a curvature. Now, you see a baby elephant sitting over here, it causes a curvature. The people standing on the surface of the Earth, this also causes a curvature. Now, question which I was discussing, that can we use Einstein's field equations to calculate the curvatures? Now, you see the entire Einstein's field equation, we can use it, but the effects would be too small to notice. That means that we need higher massive objects like Jupiter, Sun, or a black hole or a neutron star, because Einstein's field equations measures much more massive objects rather than maybe 100 elephant or 2000 elephants, or maybe a huge mass which is lying on the surface of Earth. So the answer is yes, we can measure, but the effects would be too small to notice, and we need bigger elements like black hole, Jupiter, and Sun to measure. Now when I say that it requires higher heavy objects, what actually it means by that? So you see that Jupiter and Earth and Mercury, if I take these three planets, Jupiter has got a bigger mass and it causes a bigger curvature, which is marked here in red line. So curvature is more, so the gravitational acceleration and the weight is much higher compared to that of Earth. If you see, it has got a curvature, but definitely less than Jupiter. So the gravitational acceleration is only 9.807, and the weight is also this, whereas the g for Jupiter is 24.79 meter per second square. We come to Mercury, which is a lesser curvature, and here we see that the g is even less, that is 3.7 compared to that of the weight. So from here we understand that more massive object is, the curvature is more, and what we mean by gravitational acceleration on other things in physics, this also comes from the curvature. More the curvature, more is the weight, or more is the g, and more is the dent in space-time. So now it is a quick time. So yes, the tensors actually measures the curvature. These tensors are those Ricci scalar, Ricci tensor, Riemann curvature tensor. All this actually measures the curvature. Okay, now the question is that how much is the curvature? I mean to say, if we measure something on a practical basis, right, on our daily life, we need to find out actually how much is the curvature. Okay. So here I would like to tell you that the left hand side of this equation, this part, this is called the Einstein curvature tensor, right? This can be regarded as a very complicated second order differential operator acting on the metric of space-time. Okay, this is something very quite complicated. So what does it actually tells? It describes, after a little bit of processing, the space-time's curvature, that is the tendency of the trajectories in space-time of freely falling bodies which start parallel at the initial, but they become non-parallel as the bodies move. Now all these things, now why it is becoming non-parallel, etc., are described in my further videos in general relativity, which are called geodesics. But for the time being, let us understand that if we take the Einstein field equation in this form, g mu nu, so it describes actually the space-time curvature. That means the tendency of the trajectories in space-time of freely falling bodies, which generally start at being parallel, but then starts to become deviate due to the curvature of space-time. Okay, the right hand side expresses basically, I can say it in terms of Cartesian coordinate, it would be 1 upon length square. Now here we take the right hand side of the equation. So it expresses, I would say technically in a covariant form, the distribution of energy density, momentum density and their flow in space-time. So this is the curvature, this is the distribution of energy density, momentum density and their flow in space-time. Now we are going to not look much more into details, but before we go into the curvature, this should be taken into matter. Okay. Okay, so we now come to something very important. Now this is something which I have written to emphasize the constant, this constant which converts energy density into joules per meter cube, right? That means in joules per meter cube is basically what we have done is that we have converted the constant energy here. Now here you see this one is actually converting the energy density joules per meter cube into curvature, right? So so you see, if you take 1 joule per meter cube, then when it goes into curvature, it is meter to the power -2. Right. So what does it meter per cube? So what does it actually means? That means it converts an energy density, I would say, and it takes a lot of energy density to cover into a tiny curvature. Okay, now let me take you give you through an example. So for example, we take osmium. Okay, osmium is basically what we call is the densest metal naturally found on earth, and which has got around 22.6 kilograms per meter cube, which is roughly 3 times the density of iron and twice that of the lead. Now if I multiply it by c square, why we are doing that? Because we see that the osmium has a rest energy density of 2.03 into 10 to the power 21. Okay, so joules per meter cubed. Okay, so what is happening from here is that this density actually produces only this amount of curvature. So this is the energy density. Okay, 2.03 into 10 to the power 21, that is the energy density. Okay, now see, we got an energy density of 2.03 into 10 to the power 21 joules per meter cube, but this energy density, how much this energy density produces curvature? It only produces a curvature of 4.22 into 10 to the power -22 inverse meters square of curvature. So what do we deduce from here? If we take the densest metal which is available on the surface of the earth, we multiply it by c square. So in order to get an energy density which is just 2.03 into 10 to the power 21. Obviously energy density means what? Curvature, and the result that we get in curvature is this much. So which is very small in order to measure through Einstein's field equations. So this energy density, now if I take the Einstein's field equation, you see this left part is basically the curvature produced, right? And the curvature produced is how much? 4.22 into 10 to the power -22, which is too small to be measured. And this part, the stress energy momentum tensor, which has got an energy density of 2.03 into 10 to the power 21, which we have taken as the densest material, that is osmium. So what do we deduce from here is that when you understand somebody is telling that, okay, gravity is a very weak force compared to electromagnetism, small and weak force, understand that it requires a lot of energy density to obtain a curvature. So when we talk of gravity as being the weakest force, that means that it is basically, it requires a lot of energy density to curve space-time. So to get stronger curvature, we need to go to the regimes far away from the surface of Earth. Okay, so here is a quick point which I would like to explain over here. You see that when we talk about Einstein arriving at this field equation, people seemed a little bit surprised by how ad hoc the derivation of the Einstein field equation seems to be. In essence, Einstein seemed to have decided that the source should be T mu nu, right? and on the left hand side it should be a curvature tensor, and the right hand side 2 mu nu would just match, that is the divergence free and has the right number of indices. Now I would say that is not wrong, because Einstein's original derivation to the Einstein field equation is indeed just ad hoc, as this makes a lot of meaning. Now see, the thing is that it is worth bearing in mind that the ultimate arbiter of what description should be is in terms of measurement. We should therefore regard Einstein's field equation and its prediction as hypothesis to be tested. Testing this hypothesis is still something being done today, and it motivates a lot of fundamental research in the field of science and physics. Around the time when Einstein actually formulated these field equations, other plausible formations of relativistic gravity were also proposed. Those are all found to have some kind of a flaw in important ways, but general theory of relativity can be regarded as the relativistic gravity theory that best fits in the data. There is another way of deriving the field equation, which is based on variational principle, similar the way we apply variational principle to a Lagrangian in order to describe the body's motion. So though I would say it requires further implications, it makes the simplest theory of relativistic gravity. A lot of research of these days have been done on general relativity to make it in a meaningful sense. Okay, so what we have understood right now, that it requires a lot of energy in order to take a kind of a curvature, and this curvature, in spite of their energy density, is so small that Einstein's field equations cannot predict that, and for that we need to go for some other further reasons. Okay. So now we would try to understand what is called the practical application of Einstein's field equation. Now when we talk of practical applications, the Einstein's field equation, because of its too much of complexity, requires some kind of a, I would say, normalization in the sense of quantum mechanics. But here we would say that we need to reduce the space-time and other matrix in a way so that we can understand things better. So the first thing is what is called vacuum solutions. That means we assume that there is no matter, still the space-time is being curved. The second is called weak field solution. That means gravity, and the other curvatures are slightly leviating, not much of matter or dust is present. The curvature tensors deviates in a little manner. And another is called symmetric solutions. That means there is a large portion of symmetry, for example Schwarzschild black hole or Schwarzschild metric. So symmetry means this is equal to this, is equal to this, equal to this. So more or less things are similar. So once things are similar, then we can have a little bit easier understanding of the equations and things becomes easier. Now this weak field solutions actually leads to something very important, which is called linearized gravity, and this linearized gravity gives us some of the practical applications or practical solutions of Einstein's field equation. What are the practical applications? Before that we need to understand a little bit about what we call is a linearized gravity. Okay, so what is linearized gravity? Let me tell you a basic definition. So in general theory of relativity, linearized gravity is an application of the perturbation theory to the metric tensor. As a consequence, linearized gravity is an effective method for modeling the effects of gravity when the gravitational field is very, very weak. And the usage of linearized gravity is in gravitational fields and weak field gravitational lensing. So as you can understand that we are reducing the gravity and taking it to be very weak so that the equations become easier. Now perturbation theory, as per if you learn statistics etc., this is called methods for finding an approximate solution. That means something which we are not taking the exact value because it would be too complicated. We are using a perturbation theory. So what we are doing here is that we are using the perturbation theory which is finding an approximation, and we are applying it to metric tensor. Now why we are applying it to metric tensor? Because metric tensor actually measures the causal structure of space-time. So once we apply that, things will become easier. So here you see we will consider system where curvature is very, very, very small. And the conditions are pretty simple. It breaks down into small perturbative parts, and where the metric tensor which actually is the central part of measuring the curvature of space-time, denotes a very, very small change in space-time. So we will use linearized gravity in order to understand what actually things are, so that it breaks down and becomes easier. Okay, that is basically a kind of a literal definition of linearized gravity, but here is a mathematical definition. Okay, let me explain you one by one. So this is the metric tensor we have already seen. Now, although succinct when writing Einstein notation, this is hidden within the Ricci tensor and Ricci scalar are exceptionally nonlinear. That means it is exceptionally complicated on the metric, which render the exact solution in an almost impractical, or I would say impossible way. However, when describing particular system for which the curvature of space-time I would say can be modeled into the field equation as being the Minkowski metric. So this is the Minkowski metric, right? Eta mu nu. We are using the same indices, notice mu nu, to denote space-time. So from metric tensor, we go into Minkowski metric. Now I'm not going to explain Minkowski metric right in this video, otherwise it will take a long time, but try to understand that metric tensor using the perturbation theory get reduced into something I would say something simpler, which is the Minkowski metric. And this h mu nu, which is over here, is basically the small perturbation term. So the metric tensor is being equated with the Minkowski metric, which is a little bit linear in terms of understanding. Along with that, we use the perturbation variable h mu nu, so that the perturbation theory is applied and things become easier. So we take this h mu nu as this one, which is less than equal to 1. Now what happens is that in this regime, if we substitute the general metric, okay, for this perturbation approximation results, it gives into a simplified expression of the Ricci tensor. Although it doesn't sound to be simplified, but compared to the original field equations of the metric tensor, this comes to be a little bit easier. So the Ricci tensor, which we just saw, measures the curvature and how the ball deviates from Euclidean space, is being now reduced. So the metric tensor in application with Minkowski metric and the small perturbation term gives and reduces the left hand side of the Ricci tensor. Okay, so in this way we can say that we minimize the value. So for example, this is just an arbitrary equation. So if you take this term and this term and this term and this term, and if you reduce it, then what will happen? Then the equation will become rather simple. That is basically objective of finding out a linearized gravity. Now let me explain you with another illustration. What do we mean by linearized gravity and how does it come? So it helps basically in study of gravitational waves. Okay, we are all, LIGO and other, big observatories, etc., are basically studying gravitational waves. Also, it helps in what is called the relativistic precision of Mercury. So this was done already by Arthur Eddington on 29th of May 1919, when he proved that matter causes a change in curvature, and that is why the relativistic precision of Mercury. It also helps us in modeling GPS, that is used in mobile, where when we are going or booking an Ola or an Uber, or when we are going to find out maps, etc. So all this modeling of GPS is kind of an application of linearized gravity. The second one would be calculating the orbits of Lagios and gravity probe B. This is basically a full-blown general relativistic formation, which works quite nicely on other areas. Let us see what are those. These are black holes and neutron stars. Remember that although the Earth's, I would say, gravity field, which has got a rather kind of a lumpy model, is far easier to compute with black holes and neutron stars. And also the modeling and the behavior of the solar system can also be done through Einstein's field equation. So all these, the black holes, extreme objects, neutron stars, extreme objects, modeling the behavior of the system too large, these are all being done when we find out a solution, which I just showed you through linearized gravity. Okay, here comes an important thing which nowadays we are doing a lot of research, which is called ADS-CFT correspondence. That is terms for anti-de Sitter space and conformal field theory, which is a kind of a you can say a marriage of string theory, quantum mechanics, and other. Right. So the linearized equation appears in the ADS-CFT correspondence, which is a realization of the holographic principle. It relates theory of containing gravity on a certain space, that is anti-de Sitter, to a quantum field theory living on its boundary. So the idea is that everything on the field theory has a counterpart of the gravity side. So within this framework, gravitational and waves compared to certain field theory operates on the boundary. Solving the linearized field equation allows us to extract information about them. An example we can use is useful for the formulation of the duality which exhibit confinement. Gravitational waves correspond to specific gauge invariant operators of Yang-Mills theory, that is to glue balls. So gravitational waves, in one way, ADS-CFT model, which is trying to unite string theory and quantum gravity, actually studies gravitational waves, and here we can solve the linearized equations from non-linear equation, and we can allow us to extract some information, and which helps us in further applications of the Einstein's field equation. Okay, so far so good. We understood that linearized gravity helps us in producing certain solution, but here is some of the solutions from the weak gravity metric. Okay, so the nonlinear equations actually are difficult to solve. We understand that these are very difficult to solve. So if it is difficult to solve, then we take what certain conditions and certain variable. Now when we take these certain conditions and certain variable, we reduce it from non-linear to linear, which is a form of linearized gravity. And this linearized gravity leads to solution of Einstein's field equation, which leads to weak gravity metric. Weak gravity metric means the gravity is weak, perturbation, the complications are less, the metric has been reduced, and it is easier for us to solve. Now weak gravity metric has got three ways. One is what is called the Kerr metric, then we have got the Schwarzschild metric, and we got Friedman, Lemar, Robertson, Walker metric. I am not going to explain these metrics further because it would take more time, but just understand that weak field metric or weak gravity metric has got three or many other solutions, primarily the Kerr metric, Schwarzschild metric, and the Friedman, Lemar, or Robertson, Walker metric are something which is very similar. So now you got a clear picture of nonlinear equations too difficult to solve, and then we take the certain value, we reduce it, we get a linearized gravity which leads to solution. Among them, one is weak gravity metric, and these are the further solutions. Okay, so the weak gravity metric, it's actually this simplifies the curvature tensor, allowing us to approximate terms in the nonlinear metric. Okay, so you see here when we take the weak gravity metric, space-time is not too different from the metric of special relativity. Now you understand why I was talking about Minkowski metric. The Minkowski metric was extensively used by Einstein in his special theory of relativity. So when we reduce the Einstein field equation to weak gravity, it comes to what is called something similar to metric of special relativity. This simplifies the curvature tensor essentially by allowing us to approximate terms that are nonlinear in the space-time metric as small enough as their influence can be neglected. That means it is just we are neglecting certain terms. So the solution which emerges has four non-zero metric components. These are the one. We get G00 as minus 1 plus 2 phi. We will just see what 2 phi is. It's basically the Newtonian gravitation potential, and we get this. So all the components of the space-time matrix are now 0. So the coordinates used here are x0 equals to ct, x1 will be x, x2 equal to y, and x3 will be equal to z. Okay, now let us turn the page and see what is this phi is all about. So you see this phi is basically the Newton's gravitational potential, right? And this actually works outside a spherical body of mass m centered on the origin, and it takes this form. Okay, so what we can derive from here is that the function phi, which appears as I have shown you in the Newtonian gravitational potential, it is applicable to outside a spherical body of mass m centered in the origin, and which takes this form. So finally what we can say, the famous equation of Einstein, the second order differential F equals to ma, get reduced to this one, which is the gravitational potential, and it get reduced to this one. This is what is called motion turning into geodesics. So right now what you see is basically a geodesic motion. So motion was into an inertial Newtonian Cartesian system. With the further advancement of science, Einstein further reduced it into what is called a geodesic. And the famous F equals to g m1 m2 upon r square, which is the gravitational equation for gravity, this gets reduced into 4 pi g rho, and which further gets reduced into r mu nu. This is just a short form. That means gravity now gets reduced into what we called is a curvature. So this is what we call that how we can use the field equations practically, how the weak field gravitation leads to these metrics, and how finally we saw that the motion and gravity classically gets reduced to geodesic and curvature, which is basically the cornerstone of Einstein's field equation. So let us summarize what we learned today. So first of all, we learned that what are the components of Einstein field equation. We have seen that. Further, if you want to see, you can go to my playlist in Physics for Students. What do they measure and how we measure the curvature of space-time? And we also found out that by accelerating the densest material on Earth, we get a rest energy density. In spite of that, we get a curvature which is very less. We also learned how the measurement of the scale require massive objects like black holes, neutron stars, etc. Due to the complexities, we assume the metric to be simple, and in order to make this simple, from non-linear equation we go into linear equation and finally arrive at linearity, and this linearized gravity provides us certain solutions like curve metric, Schwarzschild metric, and we also calculate what is called gravitational waves, what we call the perihelion precision of Mercury, the other factors which are gravity probes and various the GPS and other things. So that is basically a summary and an understanding of how Einstein's field equations can be used into practical, but it would require massive objects for that. I am immensely thankful to you for watching this video on my channel. Please do subscribe and click on the bell icon and to get all the notification from Physics for Students. You can also contact me at this email ID, and I have also an exclusive channel only for general theory of relativity in YouTube, which is this. If you want, you can further follow me on Instagram, LinkedIn and Facebook through those links. Thank you for watching this video. Please put up your comments and wait for yet another exciting video coming up soon on Physics for Students. Till then, goodbye.